Well, welcome to ATMOS 2750, Day 9. Our focus today is going to be on learning a little bit more about the actual Antarctic ozone hole. And we've already talked a little bit about how it was discovered, but we're going to look at how it's evolved over time. And then what was the response of scientists to the discovery of the Antarctic ozone hole? So how do we define the Antarctic ozone hole? Well, the agreed upon definition is really that it's identified as an area in the Antarctic region where the total column abundance drops below 200 Dobson units. Recall that the average total column abundance of ozone is typically 300, so we're really talking about the loss of 1/3 of the ozone in the Antarctic region. And this hole typically begins in the early spring, which is late September or early October, and persists through the end of November. So how big is it if we use that definition? Well, it started in the late 1970s and it quickly grew in size. The area of Antarctica is about 14 million square kilometers, and it exceeded that for the first time in 1984. And it's been bigger than Antarctica ever since. And so there was this period of rapid increase in the size of the Antarctic ozone hole up through about 1995. And then it's been leveled off and is slowly declining since. And we'll talk a little bit more about the response that humans had to basically cause the Antarctic ozone hole to stop getting worse and start improving. So how bad was it? Well, here we have the minimum ozone column abundance measured inside the Antarctic ozone hole as a function of time. So 1979 is when it was defined as the ozone hole started with the column abundances less than 200 Dobson units, and it quickly decreased until about 1994 when it got down to about 75 Dobson units, which is more than 2/3 of the ozone is destroyed during that time period. And then, since then, starting about 1995, 1996, it's been slowly increasing so that the minimum is not quite as bad as it had been. And now the minimum ozone concentrations are typically a little bit greater than 100 Dobson units, which still represents 2/3 loss of ozone. So what we did discover is that there's a correlation between the size of the Antarctic ozone hole and the minimum total column abundance in the middle of the ozone hole. The x-axis here is the size, and the y-axis is the total column abundance, the minimum. And you can see there's a pretty strong relationship between the two with an r² of 0.92. So before I go to the animation, I kind of want to walk you through exactly what we're looking at. So here happens to be a data that was collected from the South Pole. And every single day at the South Pole, some scientists will go out and they'll launch a balloon called an ozone sonde. And this ozone sonde will measure the pressure, the temperature, and the ozone concentration as the balloon ascends through the troposphere and through most of the stratosphere. So on the left is the current, or I should say on this particular day, are the measurements of the ozone concentrations versus height. And there's a little meter on the right of the left panel which shows the total ozone column abundance. In this particular day, it was about 130 Dobson units in late October during the time of the Antarctic ozone hole. The green line on the left panel is the maximum ozone concentration that was observed throughout the year of 2003 in this case. And on the right panel, we actually have the temperature. So the red line is the actual temperature for that given day, and then the green is kind of the reference temperature that occurred kind of on the maximum day over on the left, and then the blue is the minimum temperature that was observed during that time period. So now that you've seen the dramatic impact that the catalyst can have on completely destroying the ozone in that layer of where the ozone concentration should be maximized, you can see why scientists were so concerned. So scientists published the data showing the Antarctic ozone hole in 1985 and immediately went about writing proposals trying to be able to understand and explain why the Antarctic ozone hole was happening. And so they requested this money and received funding by 1986 because this was such an important environmental disaster for humans that we really needed to be able to solve the issue. And so then they conducted field experiments in 1986 and 1987 to test the leading hypotheses for the Antarctic ozone hole. And recall that Rowland and Molina had postulated that chlorine from chlorofluorocarbons could be a catalyst for ozone destruction, and Crutzen had identified nitrogen oxides as a potential catalyst for ozone depletion as well. And if you want to try and take direct measurements in this region, you have very limited options on how to take direct measurements because most aircraft can't fly high enough to get into the stratosphere where these measurements need to be made. And so what the scientists did is they partnered with NASA to modify a U-2 spy plane and this airplane has flies high enough, a high enough ceiling where it can actually get into the stratosphere, and it has a long enough range where it could take off from a base in Christchurch, New Zealand, and fly far enough south to penetrate the Antarctic vortex so that it could take measurements in that transition zone between outside the Antarctic ozone hole and inside the Antarctic ozone hole. And then within a short period of time, they were publishing results which showed that the ozone hole was primarily due to chlorine and that chlorine was most likely from chlorofluorocarbons, but they also identified polar stratospheric clouds as a critical element in the chemistry of the polar vortex, and that these polar stratospheric clouds are actually also necessary for ozone destruction to occur. So what are these chlorofluorocarbons? Well, they are man-made, non-toxic, non-flammable chemicals, and they contain carbon, chlorine, and fluorine, and they were first created in 1928, and they were thought to be pretty much a wonder species or a wonder chemical because they had all of these wonderful characteristics, but they also were really good at thermodynamic properties. And so they used these as refrigerants, and you might know it more commonly as Freon. It has very good thermodynamic properties, but it was also used in aerosol spray cans because you want to pressurize the spray can with a chemical or a gas that's inert, that's non-flammable, and it won't react with the species or the items in the can itself. So I thought that was a pretty good use of CFCs. But unfortunately, the CFCs have a very long atmospheric lifetime, greater than 70 years, and they also turn out to be a greenhouse gas, which means that they absorb outgoing infrared radiation in the atmospheric window, and even though they're transparent to visible radiation. So CFCs, although they have some wonderful uses, they also pose some environmental challenges because of their long lifetime, which allows them, if they get into the atmosphere, to become mixed up into the stratosphere. And they're also a source of potential chlorine into the stratosphere, which has implications as a catalyst for ozone destruction. So let's take a look at some of the CFC emission trends. So the two most common CFCs initially were CFC 12, which is the red line here, and CFC 13, which was the yellow line. And their emission was negligible, prior to 1950, but then their emissions started to rise, and it rose very dramatically between 1960 and 1970, and continued to rise all the way through the mid-1970s. And by 1960, it was about 100,000 metric tons of CFCs were being emitted to the atmosphere of CFC-12 and about 50 metric tons of CFC-13. And then later on, there were some additional CFCs which were manufactured, which were also contributing to the CFC burden in the atmosphere in the 1970s. So there were no long-term measurements of CFCs prior to the discovery of the Antarctic ozone hole. But at that point, scientists started taking measurements of CFCs around the world, and they saw that they were rapidly rising in the atmosphere. So on the left is CFC 11, and when they started taking the measurements, they ranged from 230 to 250 parts per trillion, depending upon your location. Most of the CFCs are emitted in the northern hemisphere, so it takes time for them to be transported across the equator to get to the South Pole, and that's why the South Pole numbers are lower than the northern hemisphere numbers. But everywhere on the planet where these measurements were being made, the CFC concentrations were increasing substantially still in the late 1980s. And this is parts per trillion, so 250 parts per trillion means that there are 250 molecules of CFCs for every 1 trillion molecules of air. So even though these CFCs are very rare, they are at high enough concentrations to have a significant impact on the ozone concentrations in the stratosphere on atmospheric chemistry. And you see the same dramatic rise of CFC-12s as well in the late 1980s, although it ranged from about 440 and eventually made it up to about 540 parts per trillion. So let's take a look at what the modified U-2 spy plane found. So on the x-axis, we have the latitude ranging from 64 degrees south to 70 degrees south. This represents the transition zone between the middle latitudes and the Antarctic polar vortex region. And on the top of this one, we have in the solid line, we have the ozone concentration. And in the dashed line at the bottom on the left, we have the chlorine monoxide. That's ClO. Recall that if chlorine acts as a catalyst, then that chlorine atom will react with the ozone to form chlorine monoxide, ClO. And then that ClO will then react with another ozone, and you'll end up with the chlorine back. And that's why we consider chlorine to be the catalyst. But the identification of chlorine monoxide, ClO, is an indicator that that catalytic destruction cycle is moving forward. And that's exactly what they saw. So as they crossed the polar vortex at about 67.5 or 68 degrees south, the chlorine monoxide concentrations, which had been very low, suddenly increased significantly, and the ozone concentrations decreased by about 2/3. And that is the smoking gun to indicate that chlorine is the species that was primarily responsible for the ozone destruction in the stratosphere. So the question is these CFCs and this chlorine are being emitted throughout the world, and they're getting well mixed, and they're making it into the stratosphere. So why is the ozone hole occurring over the Antarctic region? Well, in order to understand that, we have to look at the meteorology of the area. And the first step in the ozone hole formation is the formation of the polar vortex. So during winter time, when the Antarctic region essentially becomes permanently encased in darkness, the temperature gradient between the pole and the equator becomes very strong, and it develops a circulation around the continents of Antarctica that extends into the stratosphere and essentially isolates the stratosphere in the Antarctic region from the transport of air from middle latitudes. So what the polar vortex actually does is it kind of creates a wall which creates a vessel in which you have a certain amount of ozone, and if you destroy the ozone inside that vessel, you can't replace it or replenish it with ozone from outside the vessel because the polar vortex is acting as a barrier for transport from middle latitudes. So the second step in the ozone hole formation is the formation of these polar stratospheric clouds. And these polar stratospheric clouds can form if the temperature drops below about -78 degrees Celsius. So these polar stratospheric clouds, turns out, are very important locations where chemical reactions occur which transform the chlorine that's in the stratosphere from an inert form into a chemically active form where it can be a catalyst. So these polar stratospheric clouds require very low temperatures, the kinds of temperatures that you actually observe in the Antarctic region during winter. And the hydrochloric acid is basically absorbed from the atmosphere onto these polar stratospheric clouds. And this hydrochloric acid is basically coming from the chlorofluorocarbons. As the chlorofluorocarbons break down, they liberate chlorine, and some of that chlorine reacts with hydrogen to form hydrochloric acid. And that HCl is absorbed from the atmosphere onto these polar stratospheric clouds. And these heterogeneous chemical reactions can then occur on the surface of these ice crystals, and that yields chlorine gas, Cl2 gas. Now, Cl2 gas is not a catalyst. We have to have chlorine just by itself. So what you have is you build up a lot of chlorine gas during the Antarctic winter, and then when the sunlight returns in the spring, that chlorine gas, Cl2, will be photolyzed by the sunlight and broke into chlorine and chlorine. And of course, you now have this free chlorine in the stratosphere, and it can act as a catalyst, which then destroys thousands of ozone molecules before it is rendered inert through a different set of chemical reactions. So here we go. We have different reservoirs of active and inactive chlorine. So the two reservoirs of inactive chlorine are HCl, which is hydrochloric acid, and ClONO2. So these are the two primary sorts of inactive chlorine. And in the fall, basically you have these inactive forms. And 99.9% of all the chlorine in the stratosphere is essentially inactive chlorine that won't act as a catalyst. And then as you move into winter, the temperature drops, and you end up with the formation of these polar stratospheric clouds. And that's a source of chemical reactions that can convert this inactive chlorine into Cl2 gas, is the primary gas that we're going to be concerned with. And that Cl2 gas will build up until those inactive forms, those other inactive forms of HCl and ClONO2 are depleted. And it's now been converted into the Cl2, basically. And then it'll stay that way until the spring sunshine comes back, and you'll convert these Cl2 into your Cl, and that will then start your catalytic destruction of ozone, and the active chlorine will basically be reduced, and it will eventually go back into the inactive forms of chlorine through that process. And it's that process of converting the active chlorine into the inactive chlorine where the catalyzation of the ozone destruction actually occurs. So, is there any evidence that ozone is being lost outside of Antarctica? Well, the answer is actually yes. It's just not as dramatic. So here we have long-term measurements from the early 1960s, over a period of about 40 years worth of data. And you'll see that the ozone concentrations have an annual cycle. They have high periods and low periods. Basically has to do with how much sunlight is available. And superimposed on this annual cycle, there's a trend. And that trend is a decrease in the ozone concentrations, the total column abundance of ozone, of about, looks like 10, 20, 25 to 30 Dobson units over the entire 40-year time record of this sort of thing. So that's not an inconsequential amount of ozone loss. This happens to be Bismarck, North Dakota. Are there other sites that can confirm this long-term ozone loss outside of Antarctic region? Well, if we look at Switzerland, they have an even longer record, and they see the same sort of decrease, long-term loss of ozone outside of the Antarctic region due to the presence of chlorine and other catalysts in the stratosphere. So if we want to try and summarize the ozone loss, the Antarctic local ozone reductions of up to 70% were observed in the middle of the Antarctic ozone hole, and ozone reductions up to about 15% are being observed in the Arctic. And the reason that the Arctic doesn't have an ozone hole like the southern hemisphere is it doesn't get as cold, and the atmosphere, the polar vortex, is not quite as stable as it is in the southern hemisphere because of the presence of continents and oceans. And the polar stratospheric clouds right now are not very common. However, if climate change continues and the troposphere continues to warm, the stratosphere will actually get colder, which will make polar stratospheric clouds more likely to occur in the future, which could pose a threat to the ozone in the Arctic region in the future due to climate change. In middle latitudes, between 30 and 60 degrees north, ozone depletion has been detected, and the depletion of about 6 to 8% above the background concentrations that we would normally expect. And then in tropical latitudes, no ozone reduction has been observed so far. So we basically have a canary in a coal mine. We were able to identify the Antarctic ozone hole in a region that didn't have significant potential health impacts because not many people lived underneath of it. And luckily, the meteorology is a little bit different in the northern hemisphere, so the stratosphere doesn't get quite as cold, which means we don't have as many polar stratospheric clouds, which means that a lot of the chlorine remains in the inactive forms in the Arctic region. However, climate change is putting pressures on that and may cause that to change moving forward. And there has been some ozone loss outside of the Arctic and Antarctic regions that's measurable.